Hello and welcome to the Daily Space for today, Thursday, December 3rd, 2020. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain. Today, we will be joined by Dr. Jordan Stukloff to discuss a news story we covered last Friday, the orbital evolution of a new comet that will be heading into the inner solar system in the next several decades. Before we get to the interview, however, let's take a look at the news. Our first news item comes to us from the Australian Square Kilometre Array Pathfinder, or ASCAP. This new facility has imaged 83% of the visible sky. In the process, it has used only 300 hours to map 3 million galaxies in long radio wavelengths. This was possible thanks to a combination of large field of view and innovative radio receivers. At this point, this isn't a story with great science results. It's a story with great survey results. And this data set is going to be amazing. This was just a trial run. And when this is successfully launched and fully operational, which basically it is, let's face it, folks, the new data set is here demonstrating that ASCAP will be able to make the entire sky in radio wavelengths in weeks rather than years. Yes, folks, this telescope or array of radio dishes is going to be able to image the entire sky in radio in weeks rather than years. And the data that's being obtained is huge and has required all sorts of new technologies to be developed. Raw off the telescope, this new survey generated 13.5 exabytes of data. Once processed, it transformed into 70 billion pixels, 903 images, and 26 terabytes of data, containing an estimated 1 million previously unknown galaxies. This entire data set will be made publicly available through the CSIRO Data Access Portal. And in the coming years, I expect to see an onslaught of research papers that allow us to understand the evolution of the universe and its large-scale structure of galaxies like never before. What is particularly exciting to me about this data set is that in a few years, we're going to have both the capability to map the sky in radio and optical rapidly, seeing the entire sky every few nights with the Vera Rubin Observatory's Large Synoptic Telescope. This system is delayed due to COVID, but is near completion. Together, these two survey systems will have the ability to reveal the moment-to-moment amazing changes of our sky in new ways. And I suspect that no one has guessed what amazing new things will be found in the data. All right, I apparently need to go find a 60 terabyte hard drive and go play with some data.
There are basically three ways to do observational science. You can survey, as Pamela discussed. You can do targeted observations of specific objects of interest, which we'll cover in our next story. Or you can dig through the existing data to see what can be found, lurking unnoticed in all the exabytes already out there. For one intern at Johns Hopkins Applied Physics Lab, an exploration of archival data of the moon's Imbrium Basin led to the remarkable discovery of rocks on this volcanic plain that are made of minerals that may have lifted up from the lunar mantle. Over the decades, we have painted a picture of a forming moon with low-density plagioclase floating to the lunar surface, while higher-density olivine and orthopyroxene should populate the lunar mantle. Lunar rocks returned to Earth by the Apollo and Luna programs were able to demonstrate that plagioclase does indeed dominate the surface, but none of the samples found evidence of the magmatic mantle. Since all of our theories on rocky planet formation have been based on a lunar magma ocean model, the missing piece of the puzzle was frustrating to planetary scientists. The now former intern, Jordan Bretzfelder, is the first author of a new paper published in the journal Geophysical Letters that lays out her study of the Imbrium Basin. She used two different kinds of data to look for rocks that may have been brought to the lunar surface from the mantle during past lava flows. And she was able to identify two regions with large pieces of crustal material surrounded by those mantle making orthopyroxene rich materials. According to co author Rachel Klima, our understanding of all planetary evolution of solid planets builds on the magma ocean model, which was created based on the analysis of returned lunar samples. This is the first time we have found something that could be mantle, a large area measuring multiple scale blocks rather than microscopic pieces. Here is hoping that in the not too distant future, a new mission will be able to go to the moon and gather some of these chemically interesting rocks.
In our final story of the day, we're taking a deeper look at the Milky Way's nearest neighbors of notable size, the large and small Magellanic clouds. These two irregular galaxies are currently flying past our galaxy and interacting with us gravitationally. Their location makes them prime targets for exploration, and a team using the dark energy camera has released this amazing new data on these systems. The dark energy camera is on the 4-meter Blanco telescope at CTIO in Chile. Over 50 nights, a large team of astronomers obtained a 2,400 square degree data set that maps both galaxies and their surroundings. And these data sets are sensitive to objects as faint as 24th magnitude. And these images are in 5 different colors. This data will be used to understand the stellar populations of these galaxies. The scientific purpose behind this survey contributed to one of the more amusing acronyms of the year, SMASH, which stands for the Survey of Magellanic Stellar History, where both the M and A at the beginning of Magellanic are included in this smashing acronym. According to Glenn Laxton, the National Science Foundation program officer behind this survey, these are beautiful multicolor images of the Milky Way's nearest neighboring galaxies. Through the care of the dedicated team has taken, they give us a remarkable view of the 13 billion year history of star formation in these galaxies. Project co-lead Not Olson goes on to add, besides producing amazing images, these data allow us to look into the past and reconstruct how the Magellanic clouds formed their stars over time. With these movies of star formation, we can try to understand how and why these galaxies evolved. Again, this is a data release paper, and I can't wait to see the science that will be coming in the future.
And now I would like to pause a moment as we prepare to welcome our guest, Dr. Jordan Stukloff of the Planetary Science Institute. Please welcome Planetary Science Institute research scientist, Jordan Stukloff. Dr. Steckloff, thank you for joining us today.
It's a pleasure to be here to talk to you about some stuff that's been that we've been figuring out.
So we talked about your paper last week on the Daily Space, and you have found something very interesting, a centaur turning into a Jupiter family comet. Can you give us a really brief rundown of the science?
Yeah, so it's an object that was discovered about a year ago with the Atlas project. It's a series of telescopes that are looking for new things, and they found this object that seemed to share the orbit with Jupiter. And so initially, it was thought to be one of these clusters of asteroids that do share orbits with Jupiter, the Trojan asteroids, and they're just for reference. There's thought to be as many Trojan asteroids as asteroids in the asteroid belt. So it's a very large population.
Right.
But follow-up studies found that its orbit's a little weird. It's a little too close to Jupiter, and closer study revealed that it's actually in a very unstable orbit, and that a close encounter with Jupiter in 2017 put it on this orbit. It used to be much further out. And then later it was found that it had activity like a comet. So it was revealed this is a member of a class of objects that are called the active centaurs. They are objects that are migrating inwards from out beyond Neptune. And where they've been residing for billions of years, and then they spend a few million years migrating inwards until they finally encounter Jupiter.
So how does this migration occur? What makes this happen?
The short answer is gravity. The longer answer is gravity and a whole bunch of really big planets with a lot of gravity. So yeah, there's these objects that are scattered beyond Neptune in a region coincidentally called the scattered disk, which were thought to have been flung out there when early on in the solar system's history, when the planets were moving around, which is an entirely different topic that I would love to talk about. And then, so periodically these objects are in these elliptical orbits. Sometimes they come in a little bit closer to the sun, sometimes there's further away, and sometimes they come closer to the sun and Neptune happens to be in the right spot to give them just a little bit of a tug and send them cascading inwards.
So how did Jupiter change this particular comet's orbit?
Right. So yeah. So I think we actually, there's someone had this great video showing this.
Right. We do have that video.
I know part of this, but it's a great video that shows that that what happened. So these objects migrate inwards from Neptune. They're basically in a gravitational shooting gallery. You've got 4 giant planets with a lot of gravity, which very easily disturb and chaotically evolve these orbits. And this particular object had an orbit that was between, at its closest to the sun, it was near Jupiter. At its farthest point from the sun, it was a bit past Saturn. And in 2017, it happened to get really close to Jupiter, which gave it a little bit of a gravitational slingshot and changed its orbit into this weird circular orbit that is pretty strange for comets. They're usually thought to have these very elliptical orbits that take them far away from the sun and near to it.
Great. So we actually had the video. It's from Astrograv, which is, and we've watched it, once through, and it's really interesting to see how, LD2 kind of passes so close to Jupiter that orbit just completely shifts. What's going to happen to that centaur in the future? I understand that we can actually watch this orbit stabilize.
Right. So yeah. So in 2017, Jupiter put it on this new circular orbit. And only a single orbit later, it actually has another encounter with Jupiter that flings it back out into an orbit similar to what it had before it will eventually have another close encounter with Jupiter in 2063 or 2062, somewhere in the 2060s. That will eventually be the end of this object as a centaur and the birth of a new Jupiter family comet. It's going to change its orbit and fling this object effectively in our neck of the woods. It's going to come into the inner solar system, which is fun to see in its own right. But the really exciting part is what that does to the comet itself. It's now closer to the sun. Different things can happen because it's now a lot warmer.
So when we talk about, I just want to kind of clarify for the audience. So what is the difference between a centaur and a Jupiter family comet, and how are we talking about this as a transition period for it?
Oh yeah, that's a really good point. So we like to put things in boxes. We have things we call the Jupiter family comets and things we call the centaurs and the scattered disk and the Oort cloud and the Halley family comets, of which Halley is a member. But there's no really firm definition between what makes something one object and what makes something the other. And in fact, for a lot of these categories, objects slowly transition from one to the other. In the case of the Jupiter family comets and the centaurs and the trans-Neptunian objects, they're actually one continuous population. Some people started calling these ecliptic comets about a decade ago, maybe 2 decades ago.
Oh, I have heard that term in some of my research.
Yeah, and so the idea is to emphasize that these are objects that are on a continuum. The only difference between them, other than where they're located, is where they are in this migration process from out beyond Neptune toward the inner solar system. When they're in the region of the giant planets, we call them centaurs, and when they're in the region of the terrestrial planets, we call them Jupiter family comets. Okay. And so right now, it's so those are sort of just location-based definitions. And there's some more complicated definitions that we don't really need to talk about, but that's the general idea. And the exciting difference is that different things happen in each of these different regions. So we have these location-based differences, But when you're out beyond Neptune in the deep freeze of the outer solar system, there's not a lot of heat to do a whole bunch of anything. And it's only when you start getting close enough to the sun for certain ices to begin to evaporate or sublime that you can start to see this outgassing from the nucleus, from the comet itself, which can then blow dust off the surface as well. And so when we look at a comet, we're actually seeing this cloud of dust around them.
Right.
In the centaur region, dry ice, carbon dioxide, which is frozen, can start to sublime and fling dust off the surface. But in the inner solar system, it gets warm enough for water to do that. And this is important for a couple of reasons. Water is a lot more prevalent, and and when there's enough energy close to the sun, you can get a lot more activity with water. You can also have CO2 contributing. So at the end of the day, when objects come into the inner solar system, we see activity really get kicked up a notch, and we start to see a whole bunch of evolution that we wouldn't expect to see elsewhere.
So how did we first find centaurs and determine that they are this strange class between asteroid and comet?
Yeah, that's a really interesting history on centaurs. The first one discovered, I'm going to get the year wrong, but I think it was around the 1920s. It was, in any event, it was discovered by two astronomers, Schwassmann and Wachmann, and it was the first one they discovered. So it's now known as Schwassmann-Wachmann 1, as opposed to the second one they discovered, which is Schwassmann-Wachmann 2, and so on and so forth. It's not a very creative naming scheme.
Astronomers cannot be trusted to name anything.
Right. And that was the first one, and it was active, and it's actually in a very similar orbit. It's a little bit more stable, so it's going to take longer for it to move around. But it was thought, oh, there's this thing in this weird circular orbit, but it's active. It looks like a comet, so they called it a comet. And it wasn't until really the next members of the centaur population were discovered in the 1980s. I think one might have been discovered in the 70s. That this population was identified as distinct, and it was understood how it relates to the object's interior of them and outside of them. And then other larger objects were found: Chiron, Echeclus, and by the way, some of the Chiricolo, and Chiricolo is interesting because it's a centaur that has rings. There are small things with rings around them, which is something we still don't understand how they form.
Oh wow, that's great. I mean, I was just kind of getting the feel for asteroids with moons. Now we have these things with rings.
Right.
So how does this paper affect our understanding of solar system formation and evolution?
So yeah, so the interesting thing about this, so our contribution is we were looking at how this orbit evolved to get it to where it is today. And what we really wanted to know is where's this object been in the past, and has it actually spent time in the inner solar system? Because its current orbit is something that we like to call the gateway, this dynamical gateway. And we call it this because it seems that in this particular region of space, this cluster of orbits, the vast majority of Jupiter family comets first pass through these gateway region before they become Jupiter family comets. And to be clear, the inverse can happen too. Jupiter family comets can have an encounter with Jupiter that sends them back through the gateway out into the centaurs. And so we wanted to know, has this object passed through the gateway before? Which will give us a sense, has it been in the inner solar system? Has it experienced this water-driven activity that we usually think of with comets? Or is this a pristine object in the sense that it's never been close enough for water to drive activity, which means that if it were to come into the inner solar system, it would be the very first time.
And what was your determination?
So we found that it is unlikely this object has ever actually been in the inner solar system before. We can't say with 100% certainty just due to the literal chaos of this system, but with a high degree of confidence, we can say that this object has never been in the inner solar system before. And that's actually consistent with this object being as active as it is for as far away as it is. So what this means, if we put all this together, there's this object that is going to soon transition into the inner solar system. And by the way, this transition should happen in about 40 years, which for astronomers is a blink of an eye. We're used to dealing with things that are like, oh, it's going to happen soon, like in a million years. Or it just so happens that someone saw a comet inbound and you have a few days to a few weeks to plan some observations, but rarely is it on human timescales that you can actually see these things happen over the course of several years and watch this transition play out. And so what's interesting about this particular object is, since all Jupiter family comets had to migrate inwards from the Centaur region, when we look at the Jupiter family comets we've seen, we don't know how long they've been around the sun. We don't know how much they've actually experienced this in thermal environment before. But with LD2, this will be the first time it's transitioned and come into the inner solar system, which means it presents the first known opportunity to watch this activity turn on and see how these objects behave as they transition and are born a Jupiter family comet.
So what you're saying is you found your life's work.
Yeah, or someone else's life work. Yeah, there's a lot to happen here.
So
I would imagine by the time it actually comes inwards, I will be retired, hopefully still alive. I'd like to see it happen.
I feel that, because 43 years I have the same thing where it's like, oh, I could still be around for this, but
Right.
I doubt I'll be as involved.
Yeah, I hope I can still see by then.
So I have one last question, and then
Yeah.
we're gonna ask you to stick around for a little bit. But
Yeah.
my last question. So I did a lot of research on meteor showers,
Right.
and I'm curious. Do we think that this is a body that could potentially provide future meteor showers?
So the short answer is, I would imagine any Jupiter family comet could provide meteor showers. So what happens is these objects come in, they kick off all of this dust, and the dust doesn't just disappear. It forms these bands of dust that orbit the sun with the same orbit as the comet. And so anytime we see a meteor shower, what we're seeing is the Earth getting in the way of the orbits of all these dust pieces, of these particles of dust. And that's why when you look at a meteor shower, they all seem to come from a central point or radiant, because that's just where the dust band is. And that's where all this stuff is coming from on the same orbits. So LD2 certainly presents an opportunity for meteor showers. It most likely will take time for enough dust to be built up for this to become a significant shower, if it's in the right orbit where Earth can intersect it. Unless we get really lucky and just happen to pass right through the tail of this object, I would expect a pretty spectacular meteor shower in that case. But what I'm really excited about is what LD2 can tell us about all of the comets we've already seen. So there's been some very, very, very well-known missions where we sent spacecraft to comets. There was the Rosetta mission to Comet 67P Churyumov-Gerasimenko, which is a bit of a mouthful.
I'm impressed that you got that out in one shot.
Right, but and then there's been a series of other Jupiter family comets visited as flybys with the NASA. There was 81 Wilt 2, 9P Temple 1, 103P Hartley 2. There's a series of these. And but these are objects that have already been around the sun multiple times and evolved, which is one of the reasons we can plan missions to them. They have orbits that are about 6 or 7 years long. And because they come around the sun repeatedly, we can plan a mission, send a spacecraft, build it, launch it, and have an encounter. Where we can't do that with things that are coming in for the first time.
Right.
So all of our ground truth data is from what are ostensibly evolved objects. They've already responded to the heat of the sun for some significant periods of time. And what LD2 presents us an opportunity with is to understand how the activity that we've already seen on the ground of these objects relates to how they would have looked when they first came in the first time. And so what I think so not only is this the first time an object has come in, but it's going to help enable a lot of science to connect the Jupiter family comets that are well studied with the Centaur population, and ultimately with the Trans-Neptunian population, which we're only now beginning to understand and see to.
That's exciting. I'm really, it's where it's kind of like my bread and butter, is where I really like to see these bodies moving and understanding them. So I'm looking forward to more of this.
Right, and just one last piece to sort of tied into how the show started off today. This is the first object that we've identified that's going to come in that we know about, but it's unlikely to be the last. And it's very likely that we will soon discover more objects that will actually transition before LD2 actually comes in 40 years. Objects the size of LD2 should come in every few years to few decades. So this is not a rare event, but it's also, these objects are small, so they're hard to find. We're looking at something the size of a large farmer's field from a distance of 500 million miles. So it's not easy to see. And with these new telescopes that are coming on, such as the Vera Rubin telescope with the LSST, it's going to be taking pictures of the entire sky every few days. I would imagine they can see a lot of these smaller objects moving around, and maybe the smallest ones might be hard to find, but certainly some other members of this gateway population they could hopefully identify. And so I would say that, yeah, this is the first, but stay tuned because it's about to get really exciting.
I always love when we find the first, because that usually means we're on the verge of finding more of them. Now that we know they are there, we know we know what to look for.
Right. Right.
So one last question, and then I'm going to ask you to stick around. Where did you get your awesome T-shirt?
This one, I actually got this for my postdoc. I was after grad school, I was at MIT, and they have these Talk Nerdy to Me shirts with little taped glasses. And really, my entire T-shirt collection is various iterations of stuff like this. Yeah.
That's wonderful. Well, thank you for talking to us today. I'd like you to, if you don't mind, stick around, and we're going to take some questions from our audience. And but we're gonna wrap up things right now. So I'm going to welcome Pamela back on the screen, and we're gonna finish off our show, and we'll be back in just a minute with Dr. Jordan Stukloff to answer your questions too.
And pardon me while I do strange things to the video. There we go. Sorry about that, folks. I didn't mean to dissect people's heads for a moment. Production of live television and Twitch is hard. Now, I hope you'll be forgiving of one more ask. It's December, and as director of a not-for-profit project, the calendar requires me to remind everyone that we exist thanks to the generous contributions of so many of you. And these contributions are tax deductible where the law allows. Because so many of you...
Pamela, turn your sound up.
I have no sound. God damn it. I can curse because they can't hear me.
Working on it.
Oh, man.
Your mic is turned away. I think that's the problem.
No, I don't have the correct mic attached.
Ah, wrong mic. Okay. Nope.
Testing. Okay, let's go with this. Let's see if this works better. All right, everyone. I think this is working better. Thank you so much, and I hope you will forgive me for inadvertently cutting people's heads off just a moment ago. Producing live TV and Twitch streams is hard. But we're working to get better, and we're working to make you proud every day. And with this awkward transition, I find myself in the awkward position of reminding all of you that it is December. And as director of a non-profit project, the calendar requires me to remind everyone that we exist thanks to the generous contributions of so many of you. And these contributions are tax deductible where allowed by law. Because so many of you are financially able and have taken the time to give, I'm able to pay Annie, Allie, Beth, Aviva, and Rich, all the people behind CosmoQuest, for the work they do keeping everything around here going. This year, we haven't received the same level of donations we normally receive because a lot of you are not okay. I understand, and I wish I could reach out and help all of you. Please know we are here for you. If you are doing okay and you would like to see us do more here at CosmoQuest, please consider becoming part of our community at patreon.com/CosmoQuestX. Everyone here at CosmoQuest is part-time, and I'd love to give people more hours to do amazing things. We would like to add 60 new patrons to our Patreon community by the end of the year. Will you be one of them? Okay. I can stop now. This has been The Daily Space.